So today, you'll notice on the schedule that we have an assignment here. It's going to be the first homework that we've had so far. So the homeworks are structured just like the labs. The only difference is we don't have time in class to work on them. And so you'll work on this on your own outside of class. It's going to be due next Wednesday. But if you have any questions, you're obviously welcome to ask those as well. There are 3 parts. The first are just sort of starting with generally how we usually look at our data, thinking about how many observations they are, what they represent, how many variables there are, whether there's any missing data. The second is just going to be to state the assumptions of multiple linear regression, which are all the same as the simple linear regression with the exception of the linearity assumption. They still need to, basically the combination, the variables that you include in your model need to be a linear combination of y, your outcome, but the individual variables themselves don't necessarily need to have a linear relationship. And that's because you could, for example, include transformations of the variables which would meet this linearity assumption. And then finally, for that part, you need to fit the models that are described here and then create plots for each of them, the residuals versus fits and QQ plots to assess whether the assumptions are met. And if not, if it's not a testable assumption, then you could state that. And then part 2 is doing some inference. And so when we talk about doing inference, basically that means we're interested in the relationship between some explanatory variable and the outcome. So for that, you're going to report all of the beta coefficients along with their confidence intervals, and then interpret what they mean in the context of the model fit. And then exercises 5 through 7 are doing predictions. So we're going to use the same 3 models, and now we're going to choose the best one based on the R squared and R squared adjusted to select our final prediction model. And you'll state which you select and why, as well as the equation for that model. And then 6 and 7 are predicting particular values along with the appropriate confidence intervals for those. So there's an assignment set up on Canvas. So you can submit that HTML file once you finish it. All right, so we're going to start by talking about types of variables. And we've already sort of covered some of this, but we've only ever, in our models, included numeric outcomes and numeric explanatory variables. Simple linear regression and multiple linear regression always have to have numeric outcomes, so the y variable always has to be numeric or continuous or quantitative. Those are all synonymous. But the x variables actually can take on any kind of form, and so we're going to talk about that today. So there are 2 basically major classes of variables. There are numeric variables or quantitative variables, and then there are categorical variables. So quantitative, numeric variables, these are things like weight or height or year, things that have numbers. Categorical variables are things that are in categories which could either be ordered or unordered, depending on what you're measuring. So recall from the first week of class that you can use the glimpse function to see all of your variables and their types. And so here I'm looking at the Porsche price data. What are the types of variables here? They're all numerical, exactly, and we've got 2 that are double and 1 that's an integer. One thing to mention is if it had an FCT, this would be a factor. It's a type of categorical variable that we're going to talk a little bit about why a factor variable can be useful when we're fitting a model that we're trying to sort of include a variable with multiple levels in it. Here's another example. Here I'm going to look at the Star Wars data. And so what are my variable types here? What type is name, for example? Character, yeah, it's a categorical variable, exactly. And same with hair color and skin color. So that CHR is a character, it's a type of categorical variable. So as I mentioned, so far our models have only included numeric. Your book refers to these as quantitative variables. And so just to recap, what would the equation be for predicting y from x when x is numeric? What's the equation for the linear model that we use? Exactly. So y equals beta 0 plus beta 1 times x plus the error. So the question is, what would happen if x were categorical? So when x is a number, we're able to sort of minimize the sum of squared errors in order to get these betas. But what if x was equal to like apple, banana, etc.? How would we be able to fit this model? How could we mathematically do that?
Like for each category, we designate a number for it.
Exactly. For each category, we could designate a number. Now, if we had ordered categories, then we definitely could just keep one x and just have a number, like 1 for apple, 2 for banana, maybe 3 for carrot. But what that means, when we talk about, if we were trying to interpret this beta coefficient, a 1 unit change in x in this particular case wouldn't necessarily be very meaningful, because we're changing from an apple to a banana to a carrot. These are not like, so 1 unit change would imply that from an apple to a banana is going to be equal as from a banana to a carrot, etc. And this is not necessarily true for all categories. So for unordered categorical data, rather than assigning a number to each, we could create a series of indicator variables that basically allow you to say, like we could have a variable for apple that was 1 if it was an apple and 0 otherwise. And we could have a variable for banana that was 1 if it was a banana and 0 otherwise. And now this numeric variable could get plugged into this equation and we would be able to still fit our models. So that's what we're going to talk about. The equation for predicting y from x, if x is a categorical variable with 2 levels, and it's going to look just like this, depending on how many levels we have for a categorical variable, it might look a little bit different. So that's where these indicator variables are going to come into play. An indicator variable is a variable that has 2 values, usually 0 and 1, to indicate whether a data case does or does not belong to a specific category. So let's look at an example data set here. Here I've got this data this is from the STAT2 data package. This data set is called diamonds. And the goal here is to look at the relationship between the price of a diamond and some other factors about that diamond. So the outcome of interest is how much the diamond is going to cost. And we have different variables here like the color of the diamond or the carats, etc., to use to try to predict that total price. And so if we wanted to use this color variable to predict total price, as it is, if we try to just stick this in the model, it's a character variable. The R won't know what to do with that. And so we need to do some kind of transformation to create these indicator variables to allow us to use this variable appropriately. So that's what I'm doing here. So I'm taking this diamonds data set. What does the mutate function do? Exactly, it lets me add a column. And what's happening in this first line of code? What's the name of the column I'm adding? Color D, exactly. And what is that variable what will it entail? What values will it take?
1 and 0 depending on if the color is D or not.
Exactly, it'll be 1 or 0 depending on if the color is D or not. So if the color is D, then this column will have a 1, and if not, it will have a 0. What about this line of code?
If it's E, then this column would be also 0.
Exactly. So if the color is E, then this column will be 1, and otherwise it will be 0. And so I've done this for all of them, D through J, the different colors of these diamonds. And now this is what my new data set looks like. So now, in addition to having this color column, I have a whole bunch of additional indicator variable columns here that are either a 0 or a 1. So for example, for this first row, the color is E, and so it has a 0 for all of the columns that are not E, and a 1 for the column that's E. And similarly, the next row, the color is F, so it has a 0 for all of the columns that are not F, and a 1 for the one that's F. So if I wanted to model the relationship between total price and color, I could include these indicator variables, which basically have turned this categorical variable into a numeric one that R can interpret. I could include these indicator variables in my model and then see what the relationship between each of them is and the total price. So that is what I've done here. I've got total price is what I'm predicting, and I have all of my new indicator variables here on the right-hand side of my equation. Now you'll notice down here, color J ended up getting a value of NA, or missing. Why do you think color J might be missing? That's a good guess if there's no color J. It turns out there is a color J, but the problem here is that if I know the values of all of these, if I know color D through color I, if I know their value, so let's say all of those are 0, then what would color J be? If we know that these are all just indicator variables, basically of this color, if all of them are zeros, besides color J, then that means that color J must be 1. So if D, E, F, G, H, and I are all 0, then that means J must be 1, so the color must be J. So for example, you can see in this one, the color here is J. D, E, F, G, H, and I are all 0. So we can, if we know that all of those are 0, then we can perfectly predict J. And similarly, if we know any of them are not 0, so if any of them are 1, then what would J be? 0, exactly. So color J is perfectly predictable from all of the previous colors, which means that R doesn't know what value to put here because it's perfectly correlated with these other variables. And so it basically isn't allowed to fit this full model because this color J is a perfect linear combination of all these other variables that you've included in your model. So what that means is when you're including an indicator variable in a model with K, if the indicator has K categories, then you would just include K minus 1 of the indicator variables. And the one that's left out becomes the reference category that you interpret each of the coefficients for the remaining in terms of. Okay, so looking at this model where I removed color J, what is the referent category here? Yes.
Color I.
It would actually be color J since it's the only one not in this model. So what that means is that all of these coefficients are interpreted in reference to color J. That's like the baseline variable. So like this first 3,632, that would be interpreted as a diamond with color D compared to color J increases the expected total price by $3,632. So since we know that if all of these are 0, that would mean that color J is 1, or that the color is J, how would you interpret this beta hat 0, 1936? What does that mean in the context of this model? Exactly, that's the expected price for color J, or the average price for color J. So now the beta hat 0, the intercept, is interpreted as the average for the referent category. Okay, so yes.
I have a quick question.
Yes.
What is the reference category?
So the reference category is going to be the one that isn't included. And so here, like this particular variable color has 7 different categories. And so we only put 6 of the indicators in the model. The one that is not in the model is the one that the rest are in reference to. And so what that means is that like all, so for example, this right here, the 7,224, that would be interpreted as if a diamond had color, if you had 2 diamonds, one that was color F and one that was color J, we would expect that the one that was colored F would cost $7,224 more than the one that's colored J. So basically all of the coefficients end up being interpreted in the context of the referent. And the way you can tell which one's the referent is it's going to be the one that's missing from the column that isn't in the, or the category rather, that isn't in the output. So how would you interpret this, 2,423? Yes. Exactly, yes, so a diamond with color E compared to color J increases the expected total price by 2,423. Exactly. Yes?
Can you explain what the intercept means again?
Yes, the intercept is, so in any simple linear regression, or any regression setting, the intercept is going to be the expected value for Y, so the expected value for total price when all of the X's are 0. And so in this case, when all the X's are 0, that means that color is J, so because that's the referent. And so this is the expected total price when a diamond is color J. So we expect a diamond that has color J to cost $1,936. Now the fact that all of these coefficients are positive also implies that J is like the least expensive diamond because, or the least expensive color, because all the other colors, being any other color than J, increases the price of the diamond. So that's another interpretation you can get from this. Okay, what is the interpretation of a diamond with color F? What is this? What would this 7,224 be again?
Diamond with color F compared to color J increases the expected total price by 7224.
Yes, exactly. Very good. So it turns out that R is smart and you don't actually have to create these indicator variables yourself. If you put a categorical variable or a character variable on the right side of the equation, it will behind the scenes create these indicator variables for you. So the upside is you don't have to hand code it yourself, but the downside is it can be a little more opaque what the reference category is. And so there's ways to figure out, it is predictable what the reference category is. It does use like an actual system. It doesn't just pick a random one. But you have to carefully look at the output to make sure you understand what the referent is. And so when I fit this model with total price as my outcome and color as my explanatory variable, when R creates those indicator variables for me, looking at this output, what do you think the referent category is? Color D, exactly. And how could you tell it was color D?
Because it is not contained in the table.
Exactly. It's the only one that's not contained in the table. So that means that all of these coefficients are in reference to color D. So what's the interpretation of color E now, this negative $1,209?
Decreases the expected total price by 1,289.
Exactly. So a diamond that is color E compared to color D decreases the expected price by this $1,209. Okay, so what if we wanted a different referent category? Well, we could just code the indicators ourselves like we initially did and just leave the one that we would like to be the referent out of the model. Or we can re-level the factor. And so it turns out that the way that R decides what to use as the referent category is based on the levels of the factor variable. If the variable is not already a factor variable, if it's just like a character variable, it will use something like alphabetically, it might choose it that way. But we can set the levels of the factor ourselves to be able to dictate what we want the referent category to be. And so first we can look at the levels as they stand. And so it turns out by default in R, the first level of the factor is going to be what it uses as the referent. And so here, if I look at the color column from the diamonds data set, if I run the levels function on that column, I see the unique values for that column, and I also see the ordering of them as R sees it. And so it's picked D as the first level here. And so if I wanted to change what the referent would be, I could first make a new vector of levels. And so that's what I've done here in this first line. I'm creating a vector. This C here means concatenate. It just means that we're making this character vector here. It's going to have all the same values as the levels of the variable that I'm interested in re-leveling, but I'm going to put the one I want to be the referent as the first in the list, or the first in the vector. So here I'm going to have J be my referent category, so I'm going to list that first. And I'm leaving everything else in the same initial order. And then I can use the mutate function, and I could overwrite that color variable. And I'm going to use this FCT underscore relevel. What do you think FCT stands for? Factor, exactly. So this is going to re-level the factor, so FCT underscore re-level. The factor that I want to re-level is color, so this is going to be the first argument is the column that you'd like to re-level, and the second argument is the vector of new levels. And so I'm overwriting this color column to include my new re-leveled, yes? Re-level just means that like we're changing, so now instead of the levels basically are like the unique values of that factor, but they're in a certain order, and so R is always going to take the first one and use that as a reference. So re-leveling is just shuffling the order so that I'm putting the one that I want to be the referent first. So the difference between what were originally the levels D, E, F, G, H, I, and my new levels J, D, E, F, G, H, I is that J is now first. So now J will be the referent. And so now when I run that same levels function on this new updated diamonds data set, I see that J is the first one. And so now when I fit my model after updating the diamonds data sets so that J was first, what would the reference category be here? J, exactly. And you can tell both because we explicitly did it in the previous exercise, but also because it's not listed in the output. J is not here. So if the variable is binary, a binary variable is a special type of categorical variable that just has two levels. So you can just include that variable itself. You don't really have to do anything fancy with it. Let's look at a particular example. So this is using ICU data. This is a sample of 200 patients in an ICU unit. And we're interested in seeing the relationship between a patient's heart rate and whether they were admitted to the ICU via the emergency room. So our outcome is heart rate. It's in beats per minute. And our explanatory variable of interest is an indicator for emergency room admission. Is this question an inference or a prediction question, since we're interested in the relationship between two variables? It's inference, yes, exactly. Because since we're interested in the relationship, is this going to be an inferential or an inference type question? Great. Okay, so we've got this binary x variable, emergency, and our continuous y variable, pulse, which is that heart rate. I fit the model here, the linear model, and I get this output. So in the context of this model, how can we interpret this 91.11? What does that mean? Yes?
Is that the heart rate if they weren't admitted to the emergency room?
Exactly, that's the heart rate. The average heart rate or the expected heart rate if they weren't admitted to the emergency room is 91 beats per minute. And what about beta hat 1? What is that?
Like how much it increases by if they were admitted to the emergency room.
Exactly what we would expect the heart rate to increase by if they were admitted to the emergency room. So we expect that those admitted to the emergency room would have an increased heart rate of 10 beats per minute. Very good. Okay, so let's try this together. If you could go to our Studio Pro and pull in this template file here from GitHub. And we can look at the variables in the Diamonds dataset. So take a look at some of the other variables in there. Perhaps you could look at the help file for that as well. And then see if you can get the levels for the clarity variable. And then fit a model with total price as the outcome and clarity as the explanatory variable. And then I want you to fit another model where you change the referent category from what it is by default to SI1, and then refit the model. And then add depth to your model and see if you can interpret it. I'll give you a couple minutes to work on that, and then we'll do it together. All right, let's start working on this together. If I wanted to learn more about this diamonds data set, what could I do? Glimpse, yes. So I could figure out the variables by doing glimpse. So I see here there are 6 variables. We've got a couple numeric, 4 numeric, and we have 2 factor variables. I could also use the question mark diamonds, and that would pull up the help file, which would give me a little more information. I'm interested in this clarity variable, which is coded as indicated here. But also if I look at the details, it tells me what that actually means. And so it says the clarity of the diamonds ranges from IF, internally flawless, through VVS1, very, very slightly included, BS1, very slightly included, to SI1, slightly included, in the order listed above. All right, if I wanted to know the levels, as R interprets them, of these, of this variable, what could I do to see that? Yeah, I could run levels, and then what would I put on the inside? Clarity, yeah. Okay, so this gives me the levels for this variable, and notably, the ordering here is slightly different than what is listed here in the help file, so it is useful to actually check in R to see what is happening behind the scenes, like what R is going to interpret as the actual levels of these variables. Knowing what we see here, if I were to fit a linear model, what would be my referent category? Exactly, the first one, IF. All right, so let's fit that linear model. What would I put if I wanted to fit a linear model with clarity as my explanatory variable? Total price, clarity, data equals diamonds. Nice. And so you'll notice that the only one that does not have, that's not listed here is the clarity IF. So as we expected, that is the referent category. How would you interpret this intercept here, the 6,396.56? Exactly, for as a total price for a diamond, the expected total price for a diamond with clarity IF, or with a internally flawless clarity. And so that would say that we would expect a diamond with internally flawless clarity to cost $636.96. How would you interpret this negative 18.42? What does that mean? Exactly. So what this is going to say is diamonds that are slightly included 1, we expect that their average total price is $18.42 less than diamonds who are internally flawless. Great. All right, so the next exercise was to update the levels of this variable. What would I do if I wanted to do that? Yeah, so I'm going to do new clarity levels, or I could call this whatever I want. And what would I set for this object?
Copy paste the category into
What would the first one be?
oh, yeah, SI1.
Exactly, SI1, and then it's going to be all the other ones. The ordering of the remainder don't totally matter, but I want to make sure I'm writing them the same as they are in the actual current data set as well. So I've got SI1, SI2, SI3, VS1, VS2, VVS1, VVS2, and IF. So these are my new clarity levels. Now how do I apply these to the data set, or to the column in the data set? I can use mutate. So I can take the diamonds data and I can mutate it. What column am I going to? Clarity. And then what would I do? Factory level. The first argument would be clarity. And what would the second argument be? Yeah, new clarity levels. All right, so if I just run this like this, it did update the levels, although the data looks exactly the same here as it looked before, because it doesn't actually change what the values are. It just changes behind the scenes the way that R is leveling them, which for our purposes is really just going to change which one ends up being the referent category. If I wanted to actually save this, so if I were to rerun this model, it hasn't actually updated it yet. You'll notice it still is showing SI1 here, so the levels have not been re-leveled. How would I overwrite my diamonds data to make sure that it's actually saving this so when I run the model again, it will have the new levels? Yeah, so I could use the assignment to basically overwrite that diamonds data. So now it uses this new clarity that I've just re-leveled. And so now I could fit another linear model. I'm still going to have total price. It's going to look exactly the same as my previous one. But because I've made this update, it's going to have a different, it'll have a different referent category. So now for this model, hold on. Oh yeah, it did. Okay, good. So this looks like we would expect. What's the referent category here in my new model? Exactly, it's SI1. And what is the interpretation of this intercept now, this 6,378? Exactly, the expected total price for diamonds with a clarity of SI1, or the, exactly. And what about, now this was formerly my referent category. Before we interpreted the coefficient for SI1 compared to IF, you'll notice here that now the coefficient for IF compared to SI1 is exactly the same, except it's the flip of it, which that makes sense because in the one case, these models are the same, except that in the one case, we were talking about SI1 compared to IF, which reduces the price on average by $18. Whereas if we flip it, if we say we're looking at IF compared to SI1, IF would increase the price by $18. So that's going to always be the case, that if you change the referent and you look at the previous referent for that same variable, it's going to just be the flip of it. All right, the last part was to fit a model that had both clarity and depth. How would I do that? Yeah, clarity plus depth. And so now I end up with this coefficient here for depth of 322.1. How would you interpret that 322.1 in the context of this model? this was just a simple linear regression where we just had depth, how would you interpret that coefficient? Exactly, a 1% increase in depth would yield to a $322 increase in total price. So the only difference now is when you're dealing with multiple linear regression is that you have to hold the other variables included in your model constant. So we would say a 1% increase in depth would yield an expected increase in total price of $322, holding clarity constant. Great. All right. That's it for variable transformations. Let's change our types of variables. Let's switch to variable transformations now. All right, so last class we talked about this idea of trying to draw inference and how when you're interested between the relationship of variables, you would need to account for potential confounders. We're going to see that again with this particular data set. And so here, we're interested in the relationship between average SAT scores. Each observation in this data set is a state. And this it tells us the average SAT scores for students in that state, as well as the average teacher salary for students in that, or for teachers in that state. So this salary here is in thousands of dollars, and the SAT score is just the points for that SAT score. So these are averages across each of these states. And we're interested in the relationship between average SAT scores and average teacher salaries. So is this an example of inference or prediction? It is actually inference, and that's because we're interested here in the relationship. If we were interested in predicting SAT scores based on teacher salaries, then this would be a prediction model, but here we're interested in the relationship, which sort of keys us in on that we're interested in inference. Typically, the difference is when you're trying to tell the relationship between two things, we're going to focus just on the beta coefficients themselves to describe the relationship. And if we're interested in prediction, we're going to use basically the whole model to be able to help us predict like a new value. So if this question had been, how can we predict the average SAT score using the average teacher salary, then it would be prediction. Sometimes it's a little bit like the actual mechanics behind it. It's the same model either way. It's just sort of a matter of which ends up being the focus of the question. Okay, so let's say I fit this linear model, and in fact I did, where I'm predicting the average SAT score using the average salary for each of these states. So this is my model. SAT hat equals beta hat 0 plus beta hat 1 times salary. How would you interpret this result? What's the interpretation of this coefficient for salary? Yes, and so this case the salary is in $1,000 units, and so it would be a $1,000 increase in salary yields an expected decrease in SAT scores by 5 points. So what does this mean in practice? What this is saying from this model, this simple linear regression model, we are saying that we think that raising the average teacher salary actually is decreasing the SAT score. So what it's saying is that states that have higher teacher salaries on average have lower SAT scores. All right, so that may sound bad because you would sort of expect if you're paying your teachers more that the results should be better. And so this is where this idea of confounding comes in. It turns out there's a third variable here, the fraction of students that took the SAT in the state. And this is grouped here as low, medium, and high. And so we could adjust for those indicators for these groups and see how that changes our result. So the fact that this is a confounder, what we're implying here is that the proportion of students that take the SAT both influences the teacher's salary. So we think that perhaps the proportion that are taking the SAT changes the average teacher salary. And we also think that the proportion that are taking the SAT changes the average SAT score. And there's some intuition behind this because, for example, if a low percentage are taking the SAT, it's probably only the very best students who are taking it. So the average SAT score will probably be higher among states where not very many people are taking the SAT. Versus if like everybody in the whole state is taking the SAT, then the average score might be lower because there's there's a broader population that's taking this exam. Okay. So here's my model. I'm still predicting the SAT score. I've got my teacher salary here, and then I've got this frac group variable, which is just the fraction of students that took the SAT split into low, medium, and high. Looking at this output, what was my referent category? High, exactly. And how could you tell it was high? Exactly, that one was not in the output, so that means that both of these coefficients are interpreted with respect to that one. So how would you, for example, interpret this beta hat for this frac group low? What does this 150 mean?
We would expect that group to be 150.39 or 0.79 points higher than the high one.
Yes, and then there's one other piece, holding salary constant. So we would say that the expected SAT score for states that were in this that had a low fraction of people taking it, we would expect that SAT score to be 150 points higher than states that had a high proportion of students taking the SAT holding the teacher salary constant. And how would you interpret the beta coefficient for salary now? How did we interpret the beta coefficient for salary in the previous model?
One solid increase in salary led to 1.089 increase in SAT score when holding the group for the high group that carries constant.
Yes, exactly. So this would say that a $1,000 increase in average salary for teachers yields on average a 1-point increase in the SAT score, holding the fraction of students that took the SAT in that state constant. So we're going to hold that variable constant. After holding that constant, we expect that basically salary has very little impact. So 1.089, it's got just like a 1 point on average change in your SAT score compared to this coefficient, which is quite large. So it turns out that the fraction of students that are taking the exam has a much larger impact on the average SAT score compared to the average salary. And the other thing we notice here is that the average salary flipped signs. It used to be negative, but once we adjusted for this confounder, not only did it change the actual value, but it changed the sign of the value. So the interpretation of beta hat in multiple linear regression, the general form is like this. You would state the coefficient for x is beta hat, and then you would often say the 95% confidence interval. It's always good to include both the point estimate itself as well as the confidence interval. And then you would say a 1 unit increase in x yields an expected increase in y of beta hat, holding all other variables constant. Where if you were doing this in practice, you would fill in what those units were in particular. So for example, in the case of this SAT data, we would say the coefficient for average salary is 1.09 with a 95% confidence interval from -0.9 to 3.08. A $1,000 increase in average salary yields an expected increase in average SAT score of 1.09, holding the fraction of students that took the SAT constant. So if you were doing this like on a homework or a lab, for example, the pieces that are important are that you give the units both for the x or the explanatory variable and the y, and that you say something like expected or average to indicate that this is like it's from a model, it's not deterministic. And then finally that you make sure to state the specific variables that are being held constant in this model. Okay, so pictorially, this is basically what happened. When we fit this model, the first time when we only included the salary as the only variable, we get a line like this. And so the slope of this line is -5, which basically implies that increasing the average salary of teachers decreases the average SAT score. But it turns out that there's a third variable that's kind of masking this relationship. Let me zoom in on this plot just a little bit so we can see it. So here's what that plot looks like when we actually split it out by the fraction that took the SAT score. So these points are exactly the same as they were on the previous slide, but I've just colored them by the fraction that took the SAT. And so up here in green, there were the states where there was a low percentage of students that took the SAT. In blue, we have the middle, and in red, we have the high. And we can see that we've got these parallel lines here, so the slope of these lines is the same, but the intercept is different. And so basically what's happened here is we have a different intercept for each of these such that it flipped the sign of the slope when we incorporate the information from each of these groups. So this is what we mean by when we say holding the fraction that took the SAT constant within each of these groups. The beta coefficient is the same, so the slope of each of these is about 1, like we saw in our model. But the intercept is different. Kind of where that starts is like 150 points higher for the low compared to the high, for example. So what is this called where the direction of the effect reverses when we adjust for a confounder? Exactly. This is an example of Simpson's paradox. It's just an extreme example of confounding. And so notice here that the lines are parallel. So basically holding these groups constant, this is the effect that we see. But it's also possible within groups to have different slopes, and you can account for that using an interaction term. So that's what I'm going to show you in just a second. So if the lines were not parallel between groups, then that would suggest that there's an interaction present, which means that both the intercept, so where the line starts, is different and the slope itself is different. And you can quantify that via this interaction term. So to demonstrate this, we're going to look at a new data set. This is a data set that looks at growth rate for kids. And so we're going to use this weight variable as well as this age variable, which this is age in months. So this first row is not 210 years old. This is how many months this child is old. And then we're going to use the sex variable, which is the sex that these children were assigned at birth, to help us see if there's a difference in weight gain or if the growth rate differs between these groups. So here's what the overall data looks like. So on the x-axis, I have the age in months of these children, and on the y-axis, I have their weight. Just looking at this, do you think beta hat age is going to be positive or negative? Positive, yeah. So this looks like we're going to have a positive slope, which makes sense. As your age increases, so does your weight. And so now I've split them out by sex. Here we've got the blue dots are an indicator that it was a girl that was being measured, and the black dots are for boys. And if I were to fit a regression model to each of them, you'll notice the intercept is different. So basically where it would cross the y-axis here is different, but also the slope is different. And the way you can tell the slope is different is because these lines cross each other. And so that suggests that there's an interaction present. And so 2 ways you could handle this. We could just split up the data and fit a separate regression model for boys and girls, and that would be fine, and that actually would give us the same result as if we used an interaction model. But we could similarly write this in a single model with an interaction term, which would allow us to test whether that interaction is actually something that is statistically significantly present. So because the lines cross, it means there's an interaction. Another way of saying that there's an interaction is that the slopes differ based on the group. So what is the equation for this relationship? It's going to look like this, where you have your y variable, in this case weight, equals beta 0 plus beta 1 age plus beta 2, an indicator that the participant was a girl, plus this interaction term, which is going to be beta 3 times age times girl, so the interaction between these two. So let's write a little bit of this out. What would this model become for boys? So when sex is equal to 0, what would this model be? So if sex is 0 or this indicator for girl is 0, then this beta 2 is going to drop out because it's 0. And this beta 3 is also going to drop out because it'll be multiplied by 0. And so you just end up with weight equals beta 0 plus beta 1 age plus epsilon. So if you fit this model just within the boys, that's what this you would get. Now what if we fit the model, what if we set sex equal to 1 or the indicator for girl equal to 1? Then what would the model be? Yeah, beta 2 times 1, yeah. Exactly. And so we could recombine this same model to be weight equals beta 0 plus beta 2 plus beta 1 plus beta 3 times age. So this is just showing that when you fit this interaction model, it's the same as basically fitting 2 separate models, one for the boys and one for the girls, where now the intercept for the girls is going to be beta 0 plus beta 2. The intercept for the boys is just beta 0. The slope for the boys is just beta 1, and the slope for the girls is beta 1 plus beta 3. So in that context, how would you interpret beta hat 0? What does that parameter mean? For boys, exactly. So when age is 0, the expected weight for boys is negative 33.69, which is sort of a silly thing to say, but that's what the data suggests, is this negative number. Very good. And what about beta hat 2? How would you interpret that in the context of this model? Yes, exactly. So when you set for among girls, this is the change in intercept. Beta 2 would be the change in the intercept or the change in the average weight when age is equal to 0. So for a newborn girl, we would expect the newborn girl to be beta 2. I think this is maybe grams larger than a boy. And so it's the difference in the intercept between boys and girls. How about beta hat 3? How would you interpret that value? Exactly, it's the change in slope. So it's the expected change in slope between boys and girls. So how much the slope changes as we move the regression line from boys to girls. So if we were doing hypothesis testing and we wanted to test whether the slope is different between the two groups, or like another way to state that research question would be, is the growth rate for different for boys and girls, what would H naught or the null hypothesis be for that test? What coefficient do you think you could use for that? Exactly, it would be that beta 3 is equal to 0, since beta 3 quantifies the difference in slopes between your two groups. Our null hypothesis is going to be that beta 3 is equal to 0, and then what would our alternative hypothesis be?
Beta 3 isn't equal to 0.
Exactly, that beta 3 is not equal to 0. Very good. So I've used that summary function on this model to get a little bit more information. And so this outputs this little table that has my beta coefficients here, along with standard errors, t-values, and p-values. And so for that hypothesis test that beta 3 equals 0, what would be the result of that hypothesis test based on the output from this table? Yes, you reject the null hypothesis. And how did you know that? Exactly. So we're going to look at this final row, since this is the row for that beta hat 3. And we see that this p-value here is very small. It's less than 0.05. So at the 5% alpha level, we would reject our null hypothesis. So we're going to reject the null hypothesis that there's no difference in growth rate between boys and girls. So the general form of a beta hat interpretation for interactions between x and y and a binary indicator I is going to be, or rather the interaction between x and a binary indicator I is going to be this. You would first state the coefficient with the confidence interval. So the coefficient for the interaction between x and I. So in our case, this is like age would be x and I would be an indicator that the participant was a girl, is beta hat with a 95% confidence interval. This means that the effect of x on y differs by beta hat when I equals 1 compared to I equals 0, holding all other variables constant, where you would need to say this if you included additional variables in your model in addition to the x and I. So for example, here we would say the coefficient for the interaction between age and sex is negative 0.28 with a 95% confidence interval of negative 0.44 to negative 1.2. This means that the expected effect of age on weight is lower by 0.28 among girls compared to boys. All right, so that wraps up interactions. The next thing I wanted to talk about are other kind of nonlinear relationships between some outcome y and variables x. And so to address this, we can use polynomials, which basically mean like higher order terms. So for example, like squaring variables or taking the cubic of variables to try to address when you have nonlinear relationships. So returning to the diamonds data set, let's say we're interested in predicting the total price from the carrots. Is this an example of inference or prediction? Prediction, yeah, because we're interested in predicting something. And so before doing it, I plotted my data, and I saw that it looks like there's a pretty strong nonlinear relationship meaning that if I just fit the linear model, it would look like this, where it kind of looks like we're pretty systematically underestimating down here because we've got all these points that fall above, so all of our residuals up here are positive, and then we're probably pretty systematically underestimating, or overestimating rather, down here, so all of our residuals are negative, and then again up here we're underestimating. And so rather than fit this straight line to this data, we could perhaps fit a cubic or a quadratic term here, where basically we fit this curved line to account for that nonlinear relationship between carat and total price. And so to do that, I'm going to use this I here, which what that just tells R is that I want it to use exactly the mathematical formula inside the parentheses. And so what I'm saying is I would like for it to fit a model that predicts total price from carat and carat squared. And so by incorporating carat squared, then I'm allowing this to be a squared, basically a quadratic formula that will take into account that nonlinearity. So what would the equation be for this relationship? What's the equation for the model that I fit here? Yeah, y, or total price. Beta had 0, right? So which is like negative 522.7. Times the carat plus right. So if, for example, we were trying to predict the total price when carat was equal to 1.8, how would I put that in this model? Exactly, so I'd have negative 522.7 plus 2386 times 1.8 plus 4498.2 times 1.8 squared. So I would just square this term in that part. Very good. All right, so now in this context, what is the interpretation of this beta hat 1, this 2,386? This is kind of a trick question. So usually we would say beta hat is a 1 unit change in x yields an expected change in y, holding all their variables constant. But what would it mean to have a 1 unit change in carat holding carat squared constant? Yeah, both would have to change. So it's not actually possible to do that. And so what that means is when you have a polynomial term, or actually when you have any function of the x's like in your model, you need to actually specify the values you're changing between, since the change is no longer going to be constant across all values of x. So, for example, here, if let's say we wanted to say by 1 unit, we mean a change from 0.8 to 1.8. And so we've already done when carat is equal to 0.8. If we were to try to get when it's equal to, or 1.8, if we were trying to estimate when it's equal to 0.8, we could plug that in. And we could take the difference between these two numbers. Now, if we picked a different set of numbers, even if they were the same distance, so even if they were 1 unit apart, it would actually change the relationship because we have these squared terms here which update the So we can no longer talk about it just in 1 unit changes. We have to talk about specific changes in x. So here I've done it just to show you I've taken the code to do exactly this, where we take this 522, we basically plug in the whole model and take the difference between the two, and we end up with 14,081. So that would say an expected change in total price from a 1 unit change from 0.8 to 1.8 in carat would yield an expected change of $14,000. Because we're basically subtracting this constant in both cases, they cancel out. And so we can actually write this, we can rewrite this as just beta 1 hat times 1.8 minus 0.8 plus beta 2 hat times 1.8 squared minus 0.8 squared. And so this would generalize, and if this were your model where you have x and x squared, you could get the expected change for any of these, like let's say you plug in a minus b here. It will always work like this, where you could plug in beta hat 1 times a minus b plus beta hat 2 times a squared minus b squared. And this will give you the difference between, for a 1 unit change from a to b. All right, so if we changed then, so far we looked at from 0.8 to 1.8. If we instead looked at from 1.8 to 2.8, which is still a 1 unit change, but because we've got this squared term, it's going to have a different impact, so that actually changes to 23,000 as opposed to 14,000. So we can't actually talk about beta hat 1 and beta hat 2 in the context of 1 unit changes. We have to talk about it in the context of specific x values. All right, so that will finish up this on Tuesday, and then I think we'll start after that on some further ways to compare multiple linear regression models.